Hey there everyone. Today we're doing section 2 of chapter 8. We're moving on to a new section on vectors. We had a small introduction to vectors earlier, and in this lesson we're going to learn how to compute vectors when we put them on the coordinate grid. And the first thing that you want to do when you're trying to express a vector on the coordinate grid is to convert it into what's called component form. Component form is really easy to use because all vectors in component form have been repositioned with their initial side on the origin. So we're going to go ahead and do that. And for these problems, when you do them in the homework, I want you to get in the habit of, for the first time we do this assignment, I want you to always draw on a graph paper your coordinate axis, and I want you to plot the points that we're moving. Okay, eventually we'll get to some really big numbers that are difficult to graph, but for these first ones, since they're so small, I want you to get in the habit of graphing them, and then you can really see visually what we're doing when we convert a vector into component form. So for our first example, they gave us an initial point at -4, 2. So on my coordinate axis I go -4, up 2. I'm just going to label that point A. And then the terminal side B is 3, -5. So 1, 2, 3, 1, 2, 3, 4, 5. Okay, so here's vector AB. I need to draw that in. My initial side over here A to my terminal side B. And you can just tell with this notation here that B is going to be the terminal side because that's the side that gets the arrowhead on it. So now the goal for putting it in component form is we need to reposition this vector so that it is exactly starting at the origin. So with my tool I can copy this vector and very easily just move that vector to where it's on the origin. Okay, but really what did I do? I took this coordinate and I moved it 1, 2, 3, 4 units to the right and 2 units down. And I did the same thing with the B coordinate. I moved it 1, 2, 3, 4 units to the right and 2 units down. So that my new coordinate right here is 0, 0, and my coordinate down here, we'll call that B prime, is now 1, 2, 3, 4, 5, 6, 7, and then -1, 2, 3, 4, 5, 6, 7, 7, -7. Okay, so since the initial side is always going to be 0, 0 when we put it in component form, we can rewrite this vector in a completely different notation. So I can say that vector AB now is in component form, and in component form we use different symbols. We don't use parentheses because parentheses mean a singular point, but vectors we can write in component form using these angled brackets. And so I'm going to say that AB has component form 7, -7. Okay. Now you're probably wondering how I can do that without having to graph it each time. Well, it's really easy. All you do is you take the coordinates of the terminal point and you subtract from them the points from the initial point. That's what we did. We moved everything to the right 4 units and then down 2. So if I really want to think of it, my component form does have a formula. I don't want you to just memorize the formula, I want to understand why it works. The component form formula comes from taking these terminal points and subtracting from them our initial points. So we like to say that our component form will be x2 minus x1, comma, y2 minus y1. Oops, there we go, angled bracket. And remember that our initial point is technically x1 comma y1, and our terminal point is x2 comma y2. So you can take any sort of vector and rewrite it in this component form by just taking the terminal point's coordinates and subtracting from them the initial point coordinates. For this one we would have gotten 3 minus -4, which is 7, and -5 minus 2, which is -7. That's how we could get the component form of 7, -7. Okay. Try these two on your own. Okay, here's the first problem done for you. I used both the formula that we discussed and the actual coordinate axis to figure out the component form for AB. Since my initial side was at -2, -7, and my terminal side was at 6, 1, I had to move my coordinate to get my initial side back to the origin. I had to move my coordinates up 7 and over 2. So that's what I did with my terminal point here. I moved it up 7 and over 2, and I found that my new terminal point was at 8, 8, which means my component form is going to be 8, 8. If you just wanted to use the formula, you would take your initial side, which was x2, y2, and subtract x1 and y1 from them respectively. So you get 6 minus -2 is 8, and 1 minus -7 is 8 as well. So just two different ways of solving the problem. We're going to do 1b just by using the formula and not having to use the graph. So for 1b, we'd say that vector AB is equal to x2, which would be -9, minus x1, which is 0, comma, y2, which is -3, minus y1, which is 8. Just be real careful about the order that you plug those in, and be careful with subtracting negatives. So -9 minus 0 is just -9. -3 minus 8 is -11. So a vector that starts at A and ends at B would be the same direction and the same length as a vector that started at 0, 0 and ended at -9, -11. Remember that even though these two vectors are in different positions, they still have the same magnitude and the same direction. So they're the same exact value. We don't have to, it's just easier to discuss this vector in component form. Okay. The next thing we're going to talk about is how to find the magnitude of a vector. The magnitude of the vector is the length of the vector itself. And so if we have the initial point and the terminal point, the easiest way to get the magnitude is to just find the distance between the 2 points, which is using your distance formula, which I've provided for you right here. We talked about this yesterday, that this symbol, the absolute value symbol, represents the magnitude of a vector. So if we're trying to find the magnitude between 2 points, we just find their distance. So let's find the magnitude of AB. To write that, you use your absolute value brackets. You can write vector AB. And we're going to say that that magnitude will equal the square root of the difference between the x coordinates. So I'm going to do x2 minus x1 and square it, plus the difference between the y coordinates. Whoops, sorry. Let's go back. My x coordinate should have been 3 minus -4 squared, plus the difference between our y coordinates, which would be -5 minus 2 squared. So let's see, subtracting a negative, that's adding opposite, so we get that the magnitude is going to be 7 squared plus -7 squared. So we get 49 plus 49. Plus 49 is 98, so our magnitude is equal to the square root of 98. And we should probably see if we can reduce this radical. To reduce a radical, just try to think of perfect squares that will divide into it. This is divisible by 2. And look, 49 is a perfect square, so we should probably rewrite this as the square root of 49 times the square root of 2, which is 7 square roots of 2. That's the magnitude, or the length, of a vector that goes from -4, 2 to 3, -5. Okay. Try these two on your own. Okay, these are the two magnitudes for 2a and 2b. Just be real careful that you are subtracting the x coordinate from the x coordinate and the y coordinate from the y coordinate. That's it. Alright, for our last section in this lesson, for our last portion, we're going to be doing vector operations. Vector addition and subtraction is really simple. If vector A and vector B are given in component form, that's what these angled brackets mean, is this is in component form. All you have to do is correspond the components with whichever ones match and either add or subtract them. So if I have vector A plus vector B, I just take A1 plus B1 as my new added component, and A2 plus B2 as my second new component. Same thing with subtraction. If you're multiplying a single vector by a scalar, then all you have to do is distribute the scalar and multiply it to both of the components. It's really simple once you see it in practice. So let's go ahead and jump right into the example. They give me 3 vectors all in component form. So that means that the vectors start at 0, 0 and end at -4, 1. This vector ends at 2, 5, and this vector ends at -3, 0, and all of them start at 0, 0. So if we want to add 2 vectors together, since they're already in component form, this is really easy. I'm just going to take -4 for W and add it to 2 from Y. And then I'm going to do the same thing with the Y coordinates. I'm going to add 1 to 5. So my new component form, -4 plus 2 is -2, and 1 plus 5 is 6. This vector is the sum of vector W plus vector Y. If you add 2 vectors together, you should end with a vector, not a single term. Let's try B. This time they've mixed in a scalar multiplication on top of a vector subtraction. So we're going to still follow the order of operations, so I should do my multiplication first. So we're eventually going to take vector Z and subtract 2 times vector Y, but I'm going to replace Y first. Vector Y was the component form 2, 5. And so when I distribute the 2 in there, this becomes Z minus 2 times 2 is 4. 2 times 5 is 10. And now that I'm ready to subtract, I can go ahead and replace Z with its component form. Its component form was -3, 0. So I'm going to take -3, 0 and subtract 4, 10 from it. And just make sure you subtract correspondingly. So this should be -3 minus 4, 0 minus 10. You want to subtract both of the components. So we get -7, -10. Okay. 3 really simple practice problems for you. One's just a scalar multiplication. The other 2 are addition and subtraction. Try these on your own. Okay, after performing the vector operations, these should be your 3 solutions. I showed each of the steps in different colors. This one was the longest one because you had to do the distribution to each vector first, and then add these 2, and then subtract the final 2. Be careful when you subtract a negative, that's like adding. Other than that, that's it for today's lesson. Have a great one.